Hey guys, this is the Essentials of Geometry. It's our second video in the geometry series. And in the first video, we did the basics, proofs, some important definitions and postulates, etc. And now we're going to be talking about essentials, more into geometry. So some important terms. Undefined terms cannot be defined formally. That doesn't mean they cannot be defined. It's just that there's no set definition for them. An example is point, a location that has no dimension. So even though this is a definition, I mean, what does location that has no dimension mean? It's simpler to just draw a picture. This is a point. No dimensions, no length, no width, etc. Line is another undefined term. It just this. Straight, one dimension, just length, continues forever in both directions. These arrows mean that they continue forever. And then plane. It's a flat surface, two dimensions, length and width, and continues forever in all directions. So generally points are labeled with a capital letter. So this is point A. Lines are labeled line L, lowercase cursive, or they can be labeled by points that are on it. This is line AB. And planes, similarly, you can have it something like plane R, this is some fancy letter, or 3 points on it, plane A, B, C. Defined terms are terms that can be defined. So an example is the endpoint. And this is the furthest point of a finite or partially finite figure. This sounds complicated, but I'll show you examples as we define more terms, like a line segment. It's also called a segment, and it's basically part of line that has two endpoints and all the endpoints between them. So this is an example of an endpoint. It's the furthest point in this finite figure. But notice there's the partially finite example. A ray is a part of a line that consists of one endpoint and goes forever in the other direction. So this is partially finite. It's finite on this end, but it still continues infinitely there. Opposite rays share an endpoint and form a straight line. So if this is one ray, the opposite ray would be this. It forms a straight line. So some other important terms, collinear are points that lie in the same line. Non-collinear points that do not lie in the same line. Coplanar points that lie in the same plane. Non-coplanar points that do not lie in the same plane. So A and B are collinear, but A, B, and C are not collinear. In this case, A, B, and D are collinear. You can do the same thing with plane. Parallel means that they never intersect. And this could be a line to a line, like this. They never intersect. A plane to a plane, like this, or a line to a plane. I know that planes are hard to visualize because they just seem like rectangles right now, but they continue forever and they're two-dimensional. If it's a line to line, then the lines are in the same plane. So, for example, if these are two different planes and this line never intersects this line, that's not parallel because they're not in the same plane. So they have no opportunity of intersecting. Skew lines are lines that are in different planes and never intersect. So the example I just showed you, these are skew lines. Perpendicular intersect at 90 degrees exactly. So it could be line to line, like this, plane to plane, another hard visualization, with this exactly 90 degrees, or line to plane. This, where it intersects, it's exactly 90 degrees. Coincident means that they lie on top of each other. So again, it could be line, 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 plane, or plane, plane. So if I have this, and then I have another line that lies exactly on top of it, that means they're coincident. I'm not going to give you examples for plane to plane or line to plane, but it's similar to what we talked about earlier. Some important postulates, some more postulates, I should say, because we covered some in the first video. Any 2 points that lie in the same plane are always collinear. So if we have any 2 points, and let's say, oh, I forgot to switch colors. And let's say they're in the same plane, then they're always collinear. One line can pass through them. And this has to do with the postulates we talked about in the first video that says that exactly one line can pass through 2 points. Any 3 points are coplanar. If you have 3 points, even like one all the way over here, you can always draw one plane that goes through all 3. A line contains at least 2 points. That's given by the first postulate. A plane contains at least 3 non-collinear points. This is important because it could have 3 collinear points, which mean, and have a line go through them. And there could be infinite planes that pass through this. This is one example of a plane, or there could be this one that goes through it, and so on. So if they're collinear, then it doesn't have to be one plane. Through any 2 points, there's exactly one line. Ties back to this. Through any 3 points, not on the same line, through any 3 non-collinear points, there's exactly one plane. If 2 points lie in a plane, then the line containing them lies on the plane. So if we have this, then the line containing them is on the same plane. 2 lines can intersect at either a point, a line, or nothing. So the most common one, they intersect at a point. If they intersect at a line, then they're coincident. So these are coincident lines, or they can intersect at nothing. Basically, they never intersect. These are parallel lines. 2 planes can intersect at a line, a plane, or nothing. So similarly, 2 planes can intersect like this, where they intersect at this line right here. Or they can intersect at a plane, 2 coincidental planes, or they can never intersect. These 2 planes are parallel. A plane and a line and a plane can intersect at a point, a line, or nothing. So this is easy to visualize too. A point, they just intersect. A line, they're coincident, or nothing, they're parallel. If 2 lines intersect at a point, then exactly one plane contains both lines and their intersection point. How is this? We have one line, and we have another line that goes through the intersection point and another defined point. So now we have basically 3 points. This line goes through the intersection point and this point. This line goes through the intersection point and this point. So now we have 3 points, so we can define a plane. If a point lies outside a line, then exactly one plane contains both the point and the line. So similarly, this line has to have at least 2 points. And this is the third non-collinear because it's not on the same line as this. Therefore, we have 3 non-collinear points. So some more stuff about segments. The ruler postulate is really important. It says that the points on a line or segment can be matched with real numbers. So in pre-algebra, you probably learned that there's something called the real number line. And it looks something like this. So we're employing the sort of the same concept here. This is a line, and each point on the line has a real number. So there can even be like 0.1 right here. Another part of the ruler postulate says that the distance between the 2 points is the absolute value of the distance between the coordinates. So if we have 0.2 right here and 0.5, then the distance between them is the absolute value of the difference between the coordinates. So the coordinates are 5.5 and 2. The difference between them is 3.5 or negative 3.5 if you take it the other way, which is why we have the absolute value. And absolute value, as explained in our Algebra 2 and Pre-Calculus series, is the distance from a number to 0. So it's basically the positive value of that number. So this will always be 3.5. Betweenness of points, if 3 points are collinear and the middle point is this B right here, and this has, let's just say 2, 5.5, but this has coordinate 3, then B is between A and C. These all seem pretty obvious, but they're really important in geometry. 3 points are collinear if and only if one point is between the other two. So this is just an extension. Segment addition postulate. If B is between A and C, then the sum of segments A, B, and BC is AC. So if we have A, B, and C, AB plus BC is equal to AC. And this is only if A, B, and C are collinear and between. Congruent segments have the same length, and the midpoint is a point that divides a segment to congruent segments. So this can be the midpoint, and these two are congruent. Notice that a line can never be congruent, so this is not a midpoint, because this can just continue a bit more, but this doesn't. So this is not a midpoint. Instead, this is a midpoint. This has finite ending, and these are congruent segments. Segment bisector is a figure that passes through the midpoint of a segment, and the most common one is the perpendicular bisector, which is perpendicular to the segment. So if this is the perpendicular bisector, then this is the segment, and this is exactly equal. This is the midpoint. And a point is equidistant from the endpoints of the segment if it lies on the perpendicular bisector. So given this point A, B, C, this length is equal to this length. It's congruent. These two segments are congruent. Now, the coordinate plane. So plane is a two-dimensional flat surface that extends forever. Coordinate plane is a two-dimensional plane with coordinates. The x-axis is the horizontal line, y-axis is the vertical line. This should be familiar from Algebra 1, pre-algebra, etc. The origin is the intersection of the axes. Quadrants are portions of the plane formed by axes, and they're labeled counterclockwise. So now I'm going to draw a coordinate plane. So note that there are arrows here, which means it extends indefinitely. This is the x-axis, this is the y-axis, this is the origin. These are the quadrants. So this is Q1, this is Q2, Q3, and Q4. Notice that it's counterclockwise, not clockwise. An ordered pair is a location of a point on the coordinate plane. The x-coordinate is you move absolute value of x right if positive, or absolute value if negative, left if negative. So if you have 2, if the x-coordinate is 2, then you move 2 to the right. If it's -2, then you move 2 to the left. And the y-coordinate, it's similar except it's up and down. So if the y-coordinate is +3, then you move 3 up. If it's -3, you move 3 down. Some important formulas in the coordinate plane, the midpoint formula, the midpoint of x1, y1 and x2, y2, the midpoint of them is x1 plus x2 over 2, y1 plus y2 over 2. This would be a good time to pause and take notes, write this down, because this is extremely important in geometry. Distance between 2 points. Let's say we have the same 2 points, then the distance is x2 minus x1 squared plus y2 minus y1 squared. As you write this down, let me draw you a picture. If these are the 2 points, then this is the right triangle. And many of you probably know the Pythagorean theorem. And this can actually be proved using the Pythagorean theorem. Distance between 2 points in n dimensions. So if you have x1, y1, and x2, y2, and so on and so forth, it'll be x2 minus x1 squared. Or let's just say we have 3 dimensions. Then you have to use the Pythagorean theorem twice, because here's the first one, and then the second one. This is the third dimension, basically. So that formula, you can search it up online. It's pretty complicated, so I won't write it here. The distance between a point and line, this is pretty complicated to prove, so I won't prove it. But it just says that it's the absolute value of ax plus by plus c over square root of a squared plus b squared. So this is where the line has the equation ax plus by plus c is equal to 0. And the point is x, y. And this is pretty complicated. You probably don't know the equation of a line, but if you do, then you can use this formula. If not, just write it down. So angles. An angle is formed by 2 rays that share a common endpoint. So this is an example of an angle. This is one ray, this is the second ray, and this is the common endpoint. And the sides are the rays that form the angle. These two are the sides. The vertex is the common endpoint. It can be measured using a protractor in degrees. So we saw earlier that perpendicular lines form 90-degree angles. So that's the degrees. And the protractor postulate says that the sides of AOB can be matched with real numbers 0 through 180. So this can have 0 and this can have 30. And the second part of the protractor postulate says that the measure of the angle is the absolute value of the difference between them. So this is 30 degrees. Some types of angles: acute, less than 90 degrees, right, 90 degrees, exactly. Perpendicular is another name for right, as you've seen with the lines. Obtuse is between 90 degrees and 180. So these are the main 3 lines, angles. This is acute, this is right, and it's marked with a little square. And obtuse is between 90 and 180. But there are other types of angles. Like what if you go above 180 degrees? Straight is exactly 180 degrees and it's just a straight line. Reflex is between 180 degrees and 360 degrees. While full is exactly 360 degrees. And this is just a circle. So there's a straight angle. This is a reflex angle. And this is a full angle. This is not to be confused with acute angles. If you go more than 360 degrees, it would look something like this. You're going and you're going, and then you hit 360 and then you go even more. So you can just mark it as this acute angle right here. You just subtract 360. The angle addition postulate, similar to the segment addition postulate, says that if I have these two angles, this one and this one, the sum is equal to the measure of this big angle right here. That's what it says in all those complicated words. Congruent angles are angles that have the same measure. Congruent segments had the same length. Congruent angles have the same measure. An angle bisector, it divides an angle into two congruent angles. And similar to the perpendicular bisector theorem, we have the angle bisector theorem. A point is equidistant from the sides of an angle if and only if it lies on its angle bisector. So if this is an angle, this is its angle bisector. Sorry, that's unequal, but still. This is a point. It's equidistant from the sides, and it has to be on the angle bisector. This, like the perpendicular bisector theorem, is an example of a converse, is when the converse of a statement is also true. It says that if this statement is true, then the converse is also true. So this is why it's biconditional. That's why we have the if. If you don't know what either of those means, then go back and watch the first video. Adjacent angles are angles that share one side and vertex, but no interior points. So something like this. This is the side they share, but they don't share any interior points. Complementary add up to 90 degrees, while supplementary adds up to 180. So these two angles are complementary, but if you have this angle and its supplement, this adds up to 180 degrees. And these are really important in angle chasing. A linear pair is a pair of adjacent angles whose non-common sides are opposite rays. So we have this. These are opposite rays, and these are the non-common sides. What do you notice about this? This looks remarkably similar to a figure we just drew. Angles that form linear pairs are supplementary. Right, these are supplementary angles. They add up to 180 degrees. It's a straight line. This is the linear pair theorem. Vertical angles are angles whose sides are two opposite rays, and these are congruent. So an example would be this. These are vertical angles, and they're congruent. So polygons we'll talk about much later after we do circles and fun stuff like that. So, but I'll just introduce polygons a bit. So polygon is a closed figure formed by straight segments, 3 or more, and these are called the sides. Each side intersects exactly two other sides at their endpoints. So this is a polygon, but this is not a polygon because this doesn't intersect this side at its endpoint. Vertex is a common endpoint of two sides. And the number of sides is also equal to the number of vertexes or vertices. So we have 3 sides and 3 vertices. An n-gon is a polygon with n sides. A diagonal of a polygon is a segment connecting 2 non-adjacent vertices. So this is a diagonal because these 2 aren't adjacent. Convex, all diagonals are in the interior, but concave, 1 or more touches the exterior of the polygon. So this is concave, but this is convex because this diagonal is outside. This is outside the polygon. Equilateral polygon means that all the sides are congruent. Equiangular means that all the angles are congruent. And regular means that it's equilateral and equiangular. So triangle, it's equilateral because all the sides are congruent. This is equiangular because all the angles are congruent. And this is regular because the sides are congruent and the angles are congruent. Irregular, not regular, that's pretty obvious. And the perimeter of a polygon is the length along the sides. And this is the sum of the sides of the figure. So just this side plus this side plus this side. That's the perimeter. The area is the quantity that expresses what is contained inside its closed figure. This is not a simple definition, but it's basically all this space. How many blocks can fit in here? That's probably what we learned in preschool about area. And now some types of polygons. So if it has 3 sides, it's triangular. 4, quadrilateral, then pentagon, hexagon, heptagon, octagon, nonagon, decagon, dodecagon, and n-gon. Notice there's none for 11. You can just say it's 11-agon, but that's not that formal. 12 is dodecagon. There's more too, like for 20, but this is just an introduction to polygons. So that's it for today's geometry lesson. I hope you learned something more about geometry. Most of it was just a bit of review. But I'll be seeing you in our next geometry video. Bye.